Hi, today we're going to talk about arc length. And what we basically want to do is we want to find the length along this curve from this left endpoint to this right endpoint, okay? And one way you could take like a piece of string and wrap it around and try to follow the curve and then straighten it out and measure it. That's one way, but we can use calculus actually to do this. All right. So one thing I want to show you is this. Let's call this endpoint. For right now, let's call this point A. And I'm going to call it something different in a little bit, but let's call that left endpoint A and this right endpoint B. And so this point right here would be B comma f of B if this function's name is f. And this point right here would be A comma f of A. All right. And so really a crude estimate of this is we could, to estimate the length of this, is just draw a straight line connecting this to this and to this left endpoint to this right endpoint, okay? And we could use the distance formula. Now, you may not recall the distance formula, but really the distance formula is this, okay? And let me write it up here for you. And what the distance formula is, and we usually call that big D, okay? It's the square root of, all right? And in this case, it would be B minus A squared plus, and then we would do f of B minus f of A. Squared. Now really, okay, this right here is really our delta x, our change in x, and right here, this is our delta y, our change in y. So really, it's the Pythagorean theorem, right? Because this is our horizontal leg of a right triangle, and this is the vertical leg of a right triangle, and the distance between these 2 points would be the hypotenuse, okay? So that's where this comes from, all right? Now, let me help you see where this comes from. Like, how can we actually calculate the length of this and how we can get a better estimate than just connecting the 2 endpoints. So let me go to an animation I want to show you for that. So this is the animation that I wanted to show you. And this is an example of connecting the endpoints. And if we find the length, okay, just using the distance formula, we would come up with 2.79507. Right? So how can we get a better estimate for this blue shape, right? Okay, so that's really what we want to find is what's the length of this? This is a really bad estimate. So one way to do that is to partition this. In other words, to divide it up into pieces, okay? And so if we increase this and break this up somewhere, and we're going to do the somewhere in the middle here, all right? And we're going to create, with one partition, we actually are going to create 2 segments. So let me show you. Okay, so now we have one partition, 2 segments. Okay, so n is the number of segments. So right here, okay, if we find the length of this using the distance formula plus the length of this using the distance formula, we would come up with this value, okay? Now that would be a better estimate than only having 1 segment, right? Well, what if we do 3 segments? 4 segments, and see what happens is as we make more and more partitions, we're creating these segments, and what's happening is we're getting closer and closer and closer to actually being the line. And if somehow we could go to infinity, in other words, we would need a limit, right? We could actually get the actual length. So this actual animation only goes to 20. We can only create 20 segments, which would actually be 19 partitions. Okay, so we've divided this distance from A to B into 19 partitions, which actually creates one more segment than we'd have partitions. All right, so let's show how we do this with calculus. So I'm going to go back and I'll show you how we do this with calculus. All right, so what I want to do is create a partition, which means I'm going to break this length into 2 segments, okay? So what I'm going to do is with my ruler is I'm going to connect these 2. And we have to kind of start kind of small and simple to understand this. All right, so I have 2 distances that I need to find, and I need to add these together. Now I'm going to change this a to x sub 0 because it's going to make more sense to do that. All right. And so this point right here is now going to be x sub 0 comma f of x sub 0. I'm going to label this point x1. So x1 comma f of x sub 1. And this point is going to be x sub 2. So right here, this point right here is going to be the x coordinate would be x sub 1, and this one's going to be x sub 2. So this point right here now becomes x sub 2 comma f of x sub 2. We need to do this because we can't use a and b. We actually need to use subscripts because we're going to do a repeated thing in order to figure out what this is, okay? So to figure this out, I'm going to have to take this length, all right? So I'm going to take the length, and we can get the length is an approximation is by finding the distance between these 2 points, and that would be the square root of, and it would be x1 minus x sub 0 squared plus, and then this one would be f of x sub 1 minus f of x sub 0 squared. I'm going to extend my square root, and then I'm going to run out of room here, so I'm just going to kind of come down, and I need to add to this then this length, right? And so that length would look like this, the square root of, and we would take x sub 2 minus x sub 1 and square that, and then plus, and then parentheses f of x sub 2 minus f of x sub 1, and then we'd want to square that. And this is the difference in our x's, and this is the difference in our y's. Okay, so that's kind of hard to write, right? Because we're doing these, and the more of these, it's just gonna take longer and longer. I mean, I had to go down to the next line because I ran out of room over here to add it on. So how can we write this? Well, we can use sigma notation, okay? Because if you look, what's happening is this is going up by 1 each time, right? And this is always going to be 1 less than this one, right? So what we could do is we could write this formula using sigma notation. That's why I actually need the subscripts. And we're going to start it at n equals 1. And for this one, we're going to start it at 1 and we're going to end it at 2. And it's going to be the square root of, and it would be x sub n minus, now notice this one is 1 less than this one, right, each time. So if this is x sub n, this next one would be x sub n minus 1, and we would square that. I'm going to extend my square root a little bit further, and then plus, and then parentheses, and then it would be f of x sub n minus f of x sub n minus 1, and I'm running out of room even here, right? And square it and extend that, okay? So this is my difference in my x's squared plus the differences in my y's squared, and it's a formula that will generate both of these, right? So if we started at 1, this would be 1, and this would be x sub 0, this would be f of x sub 1, this would be f of x sub 0, and then we'd bump it up by 1, and we'd go to, and we'd stop it at 2. So then this would be 2, and this would be 1, and this would be 2, and this would be 1, okay? So this is a way to write this in sigma notation without having to write this twice. So, okay, what happens if we add more partitions? So this is just one partition, right? We're breaking up into 2 partitions, I should say. You know what, I said that wrong, incorrectly earlier. This is actually 2 partitions, right? 2 segments, 2 partitions, okay? Let's go to the next one. So for this one, okay, I still want to call this one x sub 0, okay? But I'm going to break this up. I want to create a point here, and I want to create a point here, and then this point right here. So if I connect these with my ruler, I would actually, this is going to create 3 segments. So 1 there, 1 here, and then 1 connecting these. And if we add the length of these 3 segments, okay, then we would get in a better approximation than we did on the last one. Okay, so this one's x sub 0, so this one's going to be x sub 1. So I'm just drawing a dashed line down. So this would be x sub 1. This would be x sub 2, and then this one would be x sub 3. 3 segments, right? So how do we write this? Write this in sigma notation. So the length, I'm going to make sure I leave myself enough room this time. So the length would be sigma. And we want to start this by making one segment. So n equals 1. And we're going to stop this at the third segment. So this is going to be the square root of, and it would be actually the same formula. So it'd be x sub n minus x sub n minus 1. Because we want to find the difference between these and then the difference and the y values of those. And so this would be squared because Pythagorean theorem or distance formula. And then plus, and then this would be f of x sub n minus f of x sub n minus 1 squared. And we're going to extend the square root. And that would be for 3 segments. So we'd start at 1 and we'd end it at 3. Okay, so that's how we'd write it. Okay, if we wanted to do 4 segments, the only difference is this would change to a 4 and we'd have 4 of these. So we'd add one more point in between the first one, the left endpoint, and the right endpoint. We'd add one more point. Okay, I've broken these up so my delta x's, my partitions, my width is always the same, but you wouldn't have to. Okay, just like integrals, all right, you don't have to make them all the same. All right, it's just convenient in order to write a formula that we make them all the same. Okay. All right, so now what if we want to do k partitions or k lengths? Okay, so right here, this would be x sub 0, which is also our left endpoint A. And then this one would be x sub k, or our last one, right? And we could also call this n, and this would be our right endpoint B. Okay, so to find the length, now I'm not going to draw them because there's going to be a whole bunch in here, but if I wanted to find any of them, what we would do to find the length, this could be approximated by, okay, taking sigma of n equals 1 to k, and this would be the formula. Okay, so the square root of x sub n minus x sub n minus 1 squared plus, and then f of x sub n, I almost wrote x sub 1 there, all right, and then minus f of x sub n minus 1, and then squared, and I'm going to extend this. Okay, but that would still be an approximation because we'd still have these line segments. So how do we make it so that it's exactly the same as this curve? Because we'd still have, like if we did 2, all right, 3, 4, 5, it doesn't matter if k is like a number like 7, right? We're going to have 7 segments. Well, there's still going to be not a complete curve, right? There's going to be error in that. So how do we clean this up? Well, we have to make this k go to infinity. So that's actually what the length is going to be. The length is actually exactly, so this is an approximation, this is exactly the limit as k approaches infinity of sigma n equals 1 to k of, and it's just the same thing, the square root of x sub n minus x sub n minus 1 squared plus f of x sub n minus f of x sub n minus 1, close parenthesis, and then square that and extend my square root a little bit further. And that would actually give us the length. But to make infinite partitions, that's actually going to be an integral, right? So this is what we're going to integrate. Now, how does this all come about, right? All right. So remember, this is our delta x, and this is our delta y. But as k goes to infinity, these get smaller and smaller and smaller. So this delta x right here actually becomes dx, and this becomes dy. All right. So what winds up happening is we have the square root of, all right, and this becomes it's delta x squared plus delta y squared, but really that becomes, because we're going to infinity and we're making these infinitesimally small, this actually becomes dx squared plus dy squared. Okay, but that's really not going to help me integrate. Okay, so let me slide this up a little bit and we'll talk a little bit more. Okay, so what is another way that I can write this? Okay, so another way that I can write this is equivalent to the square root of, and this would be dx squared plus dy squared over 1. And you're going to see in a minute why I'm going to do this, but I'm going to I can change this by multiplying by a version of 1. And my version of 1 that I want is dx squared over dx squared. And so if I bring this one, if I multiply this fraction just times this denominator, keeping this one outside, this actually becomes the square root of, and this becomes dx squared plus dy squared all over dx squared times dx squared. That's equivalent to this one. Now, what I can do with this would be dx squared over dx squared plus dy squared over dx squared. So that becomes this, the square root of 1 plus dy squared over dx squared times dx squared. Now, and I should put a bracket around this whole entire thing, okay? Because I really want to multiply this by this whole thing, right? Okay, now, because I'm multiplying, I can break this up into 2 square roots, multiplying this square root times this square root of this. Now, the square root of this is actually the absolute value of dx, but dx is always going to be positive in this case, right? Because we're taking the one on the right minus the one on the left. So this is going to become positive. So really, we don't need the absolute value. And this whole thing becomes the square root of 1 plus, and dy squared over dx squared is really just dy over dx squared times dx. And what we can do is, this is the thing that we want to integrate, and we want to start the integration at A. We want to start finding that A and into that B. So actually the arc length becomes L, and let me slide this up a little bit because I just realized you guys can't see it. L equals the integral from A to B of, and this is our integrand. It's going to be the square root of 1 plus dy over dx, dy over dx squared dx. All right, so what we need to, in order to find the derivative, right? Or sorry, not the derivative, the arc length, we need to find the derivative of dy over dx. Now, this whole thing can be replaced if our equation is in terms of x, in other words, x equals equations, not y equals equations, then what happens is this becomes dx over dy. I'm going to show you that on the next page, and this will become dy, and we're going to integrate between 2 y values, not 2 x values, because right now we're doing it between 2 x values. All right. So here we go. The definition of arc length of a smooth curve. If a smooth curve begins at AC, so that's our starting point, right? That's our left endpoint, and ends at BD, and A is less than B, and C is less than D, then the length or arc length of the curve is given by this integral if y is a smooth function of x. So smooth means there's no abrupt changes, right? No cusps, no corners, okay? Of x on A to B, right? So if you have an equation that's y equals, you're going to use this one, okay, and it's a smooth curve. And if you have an equation that's x equals, then you're going to use this one. And so the difference between this is dy over dx, and this is going to be dx over dy. And we're going to square it, right? So that's what I just showed you. This is going to be the integrand. So the difference is if y is equal to something in terms of x, we're going to need to find the derivative of y with respect to x and square it. And if x is in terms of y, then we're going to have to find the derivative of x with respect to y, okay? And this is between two x values, and this is between two y values, okay? So find the arc length of the graph of y equals x cubed over 6 plus 1 over 2x, and we want to do this on the interval from 1/2 to 2. All right, so this is actually a cubic function, okay? A little bit of problems right here at x equals 0, but if you look over here, we're not finding the length at x equals 0, so we're going to be okay on this. It's going to be a smooth curve, okay? So let's do this problem. So we have the curve at its y in terms of x. So I would rewrite this. So y is equal to 1/6 x cubed plus 1/2 x to the -1 power. And it's just going to be easier to find the derivative then if we write it like that, because it's just the power rule. All right. So dy over dx, because we're going to need that to find the arc length. This is going to be 1/6 times 3x squared plus 1/2 times -1 x to the -2. Okay, so cleaning this up, dy over dx would equal 1/2 x squared minus 1/2 or 1/2 times 1 over x squared. So the cleaner way of writing this, dy over dx, would be 1/2 x squared minus 1 over 2x squared. Okay, so we want to find this from 1/2 to 2. So the length would equal the integral from 1/2 to 2, the square root of, and it would be 1 plus, and then we need to square this, my dy over dx, so that'd be 1/2 x squared minus 1 over 2x squared, and then our dx. Okay, now I'm going to tell you, these are really, really, really extremely difficult to integrate by hand. So what we're going to do on all of these is we're going to use our calculator to find this integral, okay? All right, so let's go and grab our calculator and we'll do that. I'm just going to put it right here. Okay, so we're going to integrate this. So it's going to be alpha window, and then we want to integrate. So function integrate. So number 4, and we want to integrate from 1/2 to 2. And then we want to enter the square root, and then 1 plus, and then parentheses, and then we want to put in this, and I'd use fraction bar, 1 over 2, and then x squared. And then minus, again, a fraction bar, and then 1 over 2x squared. And then close it and square that, and then dx. And just checking, I mean, you need to be in radian, okay? And let's put this in, and we get 2.0625 or 2.063 for our answer, okay? So this is approximately 2.063. And that's how you find the arc length, all right? You got to find the derivative of y with respect to x, and then we just need to integrate in between the left endpoint and right endpoint. So for this next example, we want to find the arc length of the graph of y minus 1 cubed is equal to x squared on the interval 0 less than or equal to x less than or equal to 8. All right. So it's going to be easier if we solve this in terms of x. So if we take y minus 1 cubed, and I want to get rid of the square, so I'm going to raise both sides to the 1/2 power. And this be x squared to the 1/2 power. So this becomes y minus 1 to the 3/2 power, and this is going to equal x, all right? And so what we need to do next, so we need to find, okay, what is, because we're going to integrate from one y value to the next, and what we have is the x values. We're going to have to find the y values for these corresponding x values. So when x equals 0, right, this becomes y minus 1 to the 3/2 equals 0. And then what we could do is raise both sides to the 2/3 power. So we get y minus 1 is equal to 0. So y equals 1. So when x equals 0, y is 1 on this curve. We also need to find the y value when x is 8. So when x equals 8, okay, y minus 1 to the 3/2 power is equal to 8. So what we're going to need to do on this one is we're going to raise both sides to the 2/3 power. So the left side becomes y minus 1 is equal to 8 to the 2/3 power. So that means y minus 1. So this would be the cube root of 8, which is 2, but then I need to square it, which is 4. And then add 1, and I get y equals 5. So, all right, when x is 8, y is 5. Now, the other thing that I need to do, I have x is equal to this. I need to find the derivative of x with respect to y. All right, so if I take y minus 1 to the 3/2 power is equal to x, I want to find the derivative of both sides with respect to y. So I'm going to do that. With respect to, I wrote x out of habit, I wrote x. I need to switch this to y, right? So I wrote the wrong thing. So this needs to be dy. And then this is the derivative with respect to y of x. Okay, so since we're taking the derivative of y, and this is in terms of y, okay, it's just the power rule, right? So this is going to be 3/2 times y minus 1 to the 1/2 power, and the derivative of y minus 1 with respect to y is just going to be 1. And then this is equal to, well, this would be dx over dy. So there we have it. We have our derivative of x with respect to y. So that means our arc length for this one is going to equal the integral from, and we're going to go from y equals 1 to y equals 5. And it's going to be the square root of, and it's going to be 1 plus, and it would just be the dx over dy squared. So it's going to be 3/2 times x minus 1 to the 1/2 power, close my parentheses, and I'm going to square that. Now this wouldn't be dx over here, it would be our dy. All right, and then we could put that into our calculator. Okay, and so we press alpha window and then function integrate 4, and we're going to go from 1 to 5. Now, really, okay, it's, you're just doing an integral. So really in this, it's just easier if we write dx instead of dy, okay? You guys, and I made another mistake. I just caught it, okay? This right here shouldn't be x. I think I said it right, okay? But that should be a y right there, okay? So this needs to be y in terms of y. That's why we have a dy out here, okay? But we could do the same integral if this was x and this is dx. So that's how I'm going to put it into the calculator, okay? So we're going to do square root and then 1 plus and then parentheses. And then we're going to have a fraction, 3/2. And then parentheses. And then I'm going to use x just because it's easier, more convenient. X minus 1 raised to the 1/2 power. And we need to put a parenthesis around that. And then I need to square that. And then I'm using X instead of Y just for convenience again. And we get 9.073. So that's our arc length for this one. And that's how you find the arc length, okay? All right. So this, yeah, even up here, this looks like X, right? This should be Y's. All right, and that's it, guys, for today.